Great. All right. So today we are going to start a new module of whatever we were studying earlier. So what we were studying until now, we had studied about switch architectures, right? Just a second. So we had studied about switch architecture, and what did we see there? So we saw that this portion of the router, right? So we have the input ports here, we have the corresponding output ports, and this is the switch fabric. Okay, so this is where we had looked at, and what did we look at? We looked at first, we looked at that how this portion, this switch fabric portion, how it has changed through generations, starting from PCI bus. Then what did we have? We had a shared bus architecture. Okay, so this was a shared bus. This was the second generation. So first generation was the PCI bus. Second generation was a shared bus architecture, and then came the third generation where we had switch fabrics. Okay. So this is a recapitulation of what we have done and just how we are moving towards the next topic. So in the switch fabric, what did we see? That the closest one or the simplest one is the crossbar switch. Okay, so we had the crossbar switch here. Now, next what we found out is that crossbar switches, they have single input. You send the input here, and then you get the output out of here. Okay, so like that. So can we use more and more input in this? Can we send more and more input in this so that we make a more efficient system? So for that we had different types of multiplexing techniques. We put time slot interchanges or TSIs. Then we used space division switching. Okay, so time slot interchanges, we have seen that we put it before demultiplexing. For SDSS, we use it after that. And the simplest form of SDS was actually your crossbar. Okay. The simplest form of space division switching was actually crossbar switches. And then from there on, we have studied that how can we further improve the crossbar switches. For that, we got to multi-stage crossbar switches. Okay. So we had multi-stage crossbar switches. Then after that, we found out about the class network. Okay, and then finally we came to our Banyan fabric. Okay, so Banyan switches. Then after that we got to our improvement in the Banyan switch, which was using, what did we do? We used a sorter. Then what did we do? Sorter. Then we had a trap module. Then we had a merging module. So in this we also had a shuffler. Sort, trap, shuffle, finally merge. So this was our enhancements that we have studied up to the last class. Okay, and until Wednesday we have, until Tuesday we have done up to this. Okay, now this part of the fabric, this part, okay, this switch fabric part is, you have known by now that this is either you can have a crossbar switch Crossbar switch can have its own issues. For that, you can have either multi-stage crossbars or you can have parallel switch fabrics. You can have banyan switch, you can have parallel banyan switches, and you can also put sorter, trapper, shuffler, etc. in order to have enhancements on this part. Okay. Now, why were we doing this? Because we want to have an overall reduction in the delay here. Whenever something is entering into this system, the time that it takes to get out of the system should be as less as possible. Okay. So what do we need to do now? So now we are going to look at another part of this router architecture. Okay, so what do we know? So let us think this is the switch fabric. Now what do we know about our in general what happens? Okay, so we have buffers here at the input ports because many inputs can come at the same time and your input line speed may not be as fast. Okay, so that is why there should be input buffering, because the switch fabric may not be able to handle that much of input to send to the corresponding output port. Okay, so that is why we need some buffers at each one of the input ports. So let us name them 1, 2 to n. These are your input ports. Okay, now correspondingly we do have buffers at the output ports. So why do we have buffers at the output port? Same reason. Output line speed may not be as fast as possible, as fast as the switch fabric is actually sending out the packets. So what does the output port do? It generally has buffers where it can store these packets until they could be sent out. Okay, so for this we need some arbiter here, or we can call it as arbiter or scheduler, which will schedule these packets which are there in the output ports. Okay, all right. So today we are going to start with like how much of improvement, considering that your switch fabric works nicely. Okay, it doesn't create any issues. It does whatever its you know uh, link utilization is. How will we find out that whatever packets you are sending, whether it is going out of it, how much of it is going out to the output port? Okay, now what are we going to see today and in the next few classes is that how is this, the having buffers at these input and output ports, how is it going to help in what was our main objective, to minimize the delay. Okay, this is the objective. So in order to achieve this minimum delay for the packets which are arriving into the system, how much of these buffers are actually helping out? Okay, so this is what we are going to study now, starting with, so there can be three scenarios, right? In this, you can say when you want to check something, what do? First you check that, okay, what is the upper bound, what is the lower bound, right? We generally do that. So here what we are going to start with is, first, what is the scenario if we do not have any buffers? So the case where no buffers are there. Okay, so we will do an analysis in that case. Then second one, we will see that, okay, if I have buffers at the input ports, then only at the input ports, then how much it is helping. And the third one is that let us have the buffers at the output ports and see how much is the link utilization. Okay, so then we will see that, okay, depending upon what is the kind of link utilization you are getting, we will see that which ones should be used and why it came out to be like this, that you have buffers here too and buffers here too. Okay, So this is how we will start with. Now let me get to the slide. Okay, then I will again come back to this. The slide is visible to everybody?
Yes, ma'am.
So today we are going to start with input and output queuing. Okay, the concept of input and output queuing. So let's start with this. So this is how it looks like, right? What I drew just now. So you have your input ports here where you have, do you remember in your computer networks courses that these are actually three modules which basically work with the previous layers, right? That means PHY, data link and network layer properties, whatever they have to work with, these are there. And then you have buffers here, buffer here to actually store the packets. Okay, this is your high speed switching fabric. And similarly for the output port also, these are simply modules which work as per, your lower layers. That is network, I mean this is at the network layer, so including network, data link and file layer. So these are whatever module the packet has to go through, whatever protocols of those modules the packet has to go through, these are the ones that go through, I mean these are the modules that represent them. And we do have buffers here to actually store the packet until it can actually go out of this particular output. So it depends on what is the capacity of this line card and as to how fast it can move out the packets out of it. Okay. And we have a scheduler. We know that for switch fabric, when we were looking at, we saw that when we were getting inputs which were multiplexed, we needed to have schedulers. And also we have seen that at the output ports, when the packets are buffered, then also we need to have a scheduler to schedule them out of the output port depending upon what is the QoS that has been guaranteed corresponding to that application to the users. Okay, so this is what it basically looks like. That is a switch fabric with buffers. Okay, now as I was talking to you about that, we can also have, we will have to see that, if I am having a switch fabric with buffers at the input ports, then how it works out. If I am having buffers at the output ports, then how it works out. So like that we have to see. So this is input, this is switch fabric which is having buffers at the input ports. Okay, and there are, as you can see, there are no buffers at the output ports. So here we will do a small analysis. Okay, so before we do an analysis, let us first find out that on what on what basis are we doing the analysis, like what do we need out of this analysis. Okay, so we basically need to know that how much efficient our system is. Okay, so we have already seen, right, that sorry. So we have basically seen that this is the metric that we are basically looking at. What is the switch utilization? How much efficient is our switch? But how do we find this out? That what is the total link utilization divided by what is the total number of ports? Okay. So link utilization, how do we define it? So it is defined as the fraction of time a given link is utilized. Okay, so you can have like ports 1 to n. Okay, so what is the fraction of time that each one of these are actually getting utilized, and that summation you get here divided by the total number of ports, that will give you the switch utilization, which you will use to find out that, okay, this is, if I am having these properties, these particular properties, then it is helping me out, or it is making a more efficient system. Okay, so as a network administrator, when you will be working out, or when you will be working as a researcher, or even in companies which are basically, R&D companies which do make, routers, or which do make, or which are like Qualcomm, and which are basically working with, network devices. So Cisco, Qualcomm, etc. So these companies, when you work with, you basically need to do an analysis of, what you are making. Okay, so suppose I am making a new switch fabric, and I want to see that how much efficient it is going to be, then I would need these kind of metrics for myself. I would need to see that how much it is actually performing better. So this is just a starter for you guys to actually understand that how this works out, how can we actually do an analysis in the network. Whether you go to any other field in your careers later on, whether it is a company or in academia or in research, whatever you do, if you are in working in networks, these particular points will be always helpful for you, because unless and until you see that whether it is working mathematically, you cannot, you have to go first check that, okay, this will work, probably mathematically it looks like it is correct. Only after that you can check that, okay, fine, now let me go into the test bed, now let me see that whether it works fine or not. Okay, apart, otherwise, if you just find out that, okay, let me just find the test bed, let me just have it and then start working on it, if that happens, then many things can go wrong. So first, check with pen and paper, get your hands dirty, find out that, okay, well, whether this will work properly or not. And then after that, you go into the test bed and verify that, okay, what I have thought and what I have thought about mathematically that it is going to work. Let us see that whether it is going to work in the test bed or not. How much difference is coming because of all other practical aspects that come into picture, real-time aspects. Okay, so now let's start working with this. So we had learned about head of line blocking. Okay, so where was it? It was in the input queuing side. Okay, it should be E here. Okay, input queuing. All right, so input queuing or having buffers at the inputs. What is the problem that it shows? It shows that there can be head of line blocking. Okay, so as we have already studied in the last few classes, what is head of line blocking? That is, a packet in the head of the queue is preventing the packet behind it to be connected because of the algorithm being used for scheduling packets. Okay, now let us see. Let me just give you a small example of head of line blocking here. Okay, now suppose there is a packet. These are 1, 2, and 3. 1, 2, and 3. Okay, there's a packet here that wants to go to output port 1. There is a packet here that wants to go to output port 1. There is a packet here that wants to go to output port 3. Okay, there's another packet that has arrived at output port 3, which wants to go to input port 3, which wants to go to output port 2. Okay, 2 is free. Nobody here is asking, nobody in these input ports is asking for output port 2. So actually 2 is free. It can take this particular packet. But what's happening? There is a contention between this guy, that is input port 1, and this guy that is at input port 3 for the same output port, that is output port 1. Okay. So now suppose So there is a contention here. So suppose this guy got the chance to transmit its data to output port 1. So that means here this guy will wait, assuming that you have FIFO scheduling. That means one after FCFS, I mean one after the other it will come as per their arrivals. So here this guy will wait until this contention goes off. But at this particular time instance, this output port is basically idle. It is not doing anything. But if this guy could have been given the first chance here, this guy could have been given the first chance here, then the switch utilization would have been maximum. Okay. So that is the issue. This is known as head of line blocking or HOL blocking. I hope this is clear with you. All right. So for with when you have input queuing, this will be one of the issues. Okay, that is head of line blocking can happen. Okay, so given the issue that we are seeing here, that with input queuing and with FIFO scheduling, we are getting such issues such as head of line blocking. So with that, it has been found out that theoretical maximum switch utilization with input queuing is about 58%. Okay, so we will actually in this course we will actually find out that how we get this 58%, but we will go slowly towards that. Okay, so for now let's just get to know about this much, that theoretical switch utilization, maximum switch utilization with input queuing is actually about 58%. So only 58% of the switch is getting utilized. Okay, so very less efficient as you can see here. Now let's see that what happens with output queuing or output buffering. Okay, so that means we are just having the scenario, everywhere the spelling is wrong. Okay, so we are just having the scenario that we have the input ports here and we have the output ports. There are no buffers here, and in the output port we do have buffers. Okay, so we are going to check that with this output ports having buffers, how is it going to perform. So what happens, let's see what happens, what are the basic features when we are looking for output queuing. So first is that scheduler needs to be there. Okay, we know that whenever we are talking about output line cards, if we are having a buffer, then we need to have schedulers there, because if you have packets and they have different QoS constraints, so for that you need to have a scheduler to actually schedule these packets. So you can have per line card scheduler also, or you can have simply one scheduler which can work for all of these line cards. Okay, so that is one thing. Then what is required from the switch fabric side, that the switch fabric has to operate n times faster than the input link. Okay, we are assuming that input link is not having any buffers. Okay, so switch fabric has to operate n times faster than what the input link's capacity is. Okay, so that is the task required from the switch fabric side for output queuing scenarios. Then what is the issue? Can there be any problem with this? So there can be. We have already seen that when all packets are wanting to go to the same output port, in that case there will be contention for that particular output port. Okay, how can we reduce that? We can reduce that by having a switch fabric which can work very fast. Okay, which can work very fast to send these packets to the particular output port. Okay, now let me show you here what I'm talking about. So this is input ports. These are the different input ports. These are the different corresponding output ports. So what I'm saying here is that, so this is 122N, this is 122N. That if all the packets are basically destined to this particular output port, suppose output port 1, then your switch fabric must work very fast so that whatever output input is coming from this side, it can actually take it and it can store it in these buffers at the particular output port. Okay, so that's what is needed. So in this case, what will happen? If your switch fabric works fast enough, then whatever input is coming, whether it is coming to the same output port or not, you can actually send them and you can store them in this output port buffer. So this will not reduce your entire switch utilization. Your switch utilization is happening faster only. Okay, only thing is these will get buffered and then the scheduler will actually work out as to my handwriting. Just a second. Eraser. Yes. Okay, fine. Just a second. Just wait a second. Where was I? I don't know why. Just a second. Let me do it in the Word file then. Hmm. So you have the switch fabric, you have the input lines here, you have the corresponding output port buffers. Okay, so if there are many packets that are arriving to this particular output port and you have a buffer here, if your switch fabric works fast enough, the utilization of the switch is high because they are all getting moved from this switch to their corresponding output ports. The destination is the output port. Okay, then there is the task of the scheduler to actually schedule these packets which are there in this buffer one by one. All right, so this is what we are basically looking for as to if we are having output port buffering, then what is needed in this case. Okay, so this is the case. Then what's the next one? That when all n packets at the input port has, okay, this we have already done. Then with this, if we have a faster switch fabric and we have buffers at the output port, then theoretically it is supposed to give you the maximum utilization. Okay, so theoretically it is supposed to give you the maximum switch or link utilization, that is about 100%. Okay, but whether in general this happens or not, that we need to see, and how can we make this happen. Okay, or at least, if you cannot get something 100%, you at least try to get, approximately as maximum as possible of it. So that's what we need to see. So today what I'm trying to tell you all in this class is that, what is that we need to do, how do we need to find out. Okay, and how we find out exactly, how do we get our hands dirty, that we will see one by one. This is about output queuing. So now let's see about the scenario where we do not have any buffering. Okay, that is, there is no queuing, and with that, how much of link utilization you are going to get with simple input and output ports. Okay, so let us see. So for this, in order to find out that what is the performance evaluation of a switch which is having no buffers, that means a bufferless switch, how do we find out that what is the theoretical maximum link utilization for such kind of a switch? Okay, when we find this out, then we will see that which one works better and how does it work better. You have already seen that theoretically it has been found out that for output ports 100% and for input ports it is 58%. So let us see what a bufferless switch, I mean how much is the link utilization for a bufferless switch. Then we will see about the other types, that is input ports, input queuing and output queuing. Okay, so assumptions, you have to first see what are the assumptions. So you have an input and an output ports. We assume that we have fixed length packets. Okay, so that is another thing. Then what do we need to say here? Another assumption. So we divide time into slots. Okay, so that is why it is given out as slots. So we have divided the time into slots, and then in one slot you can actually send one packet. Okay, so that means whatever your packet length is, that will be sent in one time slot. Okay, so that is why it is written as one slot equals one packet length. Okay, so please let me remind you, this is the scenario that we are talking about. We have input ports here and we have output ports here. None of them is having buffers, and this is your switch fabric. Okay, so one slot you can send one packet. Let us assume that the packet length is fixed. Okay, this is an assumption that we are making. Now what else? Now let P be the probability of packet arrival per time slot per input port. Okay, so this is the probability. P is the probability of packet arrivals per slot per input port. Switch capacity, we know what is switch capacity. It is defined as the number of packets that the switch can send per time slot to the corresponding output ports. Okay, so that is what the switch capacity is. It is the number of packets that the switch can send per time slot. Okay, so how can you find out what's the maximum switch capacity? N packets per time slot. Given that you have one slot, means one time slot you are sending one packet, okay, of a given packet length, and n is the total number of input and output ports. So maximum switch capacity should be n packets per time slot. Okay, now we are considering a uniform distribution for the arrival of packets. Then a packet can be destined for any one of the n output ports with equal probability, that is 1 upon n. Okay, so these are the assumptions that we are having. Now we will get to the next part of it. So let us assume that we have an input port J. Okay, what was the probability that we found out? P is the probability of packet arrival per slot per input port. Okay, probability that this input port J is having a packet is P. Okay, now probability that it goes for a particular output port I is P by N, because packet can be destined for any one of the n output ports with equal probability 1 by n. So this is the value here. Now probability that the packet does not go for a particular output port I is of course 1 minus P by N. Probability that the output port I is idle in a time slot will be 1 minus P by N power N, right? So what would be the probability that output port I will transmit a packet in a time slot? That will be equal to 1 minus 1 upon, 1 minus 1 minus p by n power n. Okay, so this was probability that the port I is idle in a time slot, and this is the probability that it will transmit a packet in a time slot, and that is given by 1 minus p by n power n. Okay, so this is what it is giving you, the probability that the output port I will transmit a packet in a particular time slot. Okay, so if you find out that for whatever number of output ports you are having, okay, so this is for all for a given output port I, what is the probability that you can your output port, any output port I will transmit a packet in a time slot. So that means it is essentially what, it is essentially equivalent to your link utilization. That means how much of the link is getting actually utilized. Okay, so therefore utilization for output port I is given by this factor 1 minus p by n power n. Okay, now let us get further into this. So for the entire switch, if you have n input output ports, then the switch utilization will be given by n times of this value, that is 1 minus p by n power n. Okay, I think up to this it should be pretty clear on this one. So if we normalize it with respect to the maximum switch capacity, what do we know about maximum switch capacity? Summation of link utilization for all ports divided by the number of ports, right? So that's it. That's given here, and that equals to this value, right? Simply 1 minus p by n power n. Okay. So now, how do we find out the theoretical maximum value? So if we consider p equals to 1, okay, which is the best we can think of for a probability. So if we consider p equals to 1, then for n equals to 1, that is if you have only one port, then your switch utilization becomes equal to 1, right? If you think that there is anything, if you disagree with it, you can ask me. Okay, so this is your switch utilization if you have only n equals to 1. Now let's see for different n's, how much do we get? For n equals to 2, your switch utilization will become how much? 1 minus half power 2, right? So that gives you this value. Similarly, if suppose I get n equals to 4, my switch utilization will become 0.68 after calculations. Okay, so what if I now make n equals to infinite? Okay, so how are we getting this value? When n tends to infinity. Okay, so that means when limit n tends to infinity, then this value, that is 1 minus 1 by n, p equals to 1. You should know that p equals to 1. Okay, we have already considered, we are doing this for p equals to 1 here. So when limit n tends to infinity, 1 minus 1 by n power n, then this value is equal to e power minus 1. So use this here, and then you will get this value, that is 0.63. That is, when you are having no buffers, you are getting 63% utilization of the switch. Whereas, what have we studied? When we were using input buffering, when we were having that, the theoretical utilization comes out to be 58%. So, having a buffer is actually bad as compared to having no buffers. Okay, so this is a very interesting question that you can think of, that why is this happening? If I am having no buffers, I am still having better utilization, whereas if I am having input buffering, I'm having a lower utilization. So this I want you all to think about it. Okay, so maybe next when you actually go ahead and see that how it works out further, you will get an answer. But as of now, how much you know, please think of this answer, why this is 63% and why with buffering you are getting 58%. However, if you are having the buffer at the output port side, you are having 100% utilization. Okay, so this is a very interesting inference, and I would like you all to think about it. All right. So I hope that up to this part is clear. Is this clear to everybody? I will then get into the next part. Okay. This is the end of this slide. Okay. Where is the Word file? All right. So now we have done up to input ports. Sorry, up to no buffering. All right. Okay. New page. Is it not coming? Now, we have studied about the situation where there is no buffering. Okay. And we have also seen that if we have output buffering, then with certain given conditions, you can get up to 100% theoretical utilization. Practically what is happening that we will see further later on, but theoretically you can get up to 100% utilization. Okay. And we've also seen that theoretically input buffering or input port queuing, that gives you approximately 58% utilization. And this guy gives you 63% of utilization. Okay, we have seen with analysis how it gives 63%. We should also see with analysis how this gives 58%, isn't it? But how do we get the analysis being done? We have a scenario where we have buffers and packets are arriving here. This is your switch fabric. Okay, so packets are arriving here. What is the arrival? That will also affect this. After the arrival, how many packets are in this system? That will also affect that, how fast the packets can be moved from input port to the switch fabric and then further to the output port and then finally clearing it out. So if we are checking from the input buffer side, we are basically limited by the arrival rate of the packets. Okay, then how fast then what how many number of packets are actually in the system when your new packet is entering into this, because that will determine that how fast you will actually get out of the system, assuming that you are currently using FIFO. Okay, so that is one thing. So what is the total number of packets in this? And then what else will affect here? That how fast is this line card actually? Okay, what is the capacity? So that means how fast your packets can be served when they are moving out of this buffer to this particular switch fabric. Okay, so that means what is the service rate per packet? Okay, so this is how your analysis or these are the factors which will affect your analysis of how much will be your theoretical utilization. But how do we find this out? We need to find out now that what is the delay here, what is the number of packets which are basically waiting, how many jobs can be actually sent out, or how many packets can be actually sent out from this particular port. Okay, so we need to find out some way in order to just get a hang of how this switch is going to work out. So simple mathematics is not going to help you out in this. What is going to help you out for this very bad line? Okay, anyways, um, what is going to help you out? We are going to look at something very interesting, and that is queuing theory. Okay, what is queuing theory? Queuing theory is basically a mathematical tool. Okay, it is a mathematical tool that helps you to analyze systems where jobs, or if you say network systems, then packets, where jobs basically enter the system, they wait for some time and for getting served, and then after that they get served, they move out of the system. So for example, you have, whenever you go to you catch a flight, you have your, your counters are there, no, counters for boarding passes like this. Okay, and there are queues. So there is a single queue most of the time, okay, for a particular airline. Suppose this is Indigo. Okay, so this is a particular queue where different people are basically waiting, and these are the people who are basically giving you the boarding passes. Okay, so 1, 2, 3. Okay, so what happens? One person comes in front of the queue, and depending upon which of these counters are free, it will go to that particular counter. It will get served, and then it will then the person will go out and join the actual line for security. Okay, so we are talking about the system up to this. That means how fast. So how much time will a person require in this particular system? Okay, it is a queued system. People are getting queued because why? Because these people are serving and there are too many people here. So the rate at which they are serving is actually pretty less. So and they're serving one by one here. So therefore there is a queue. People are waiting in the queue, and then once the job is done at this place where they're getting their boarding passes, then they are going out of the system. Okay, so whenever there is a new person, that is you, suppose you are arriving, let me call it Y. Suppose there is a new person Y arriving here. So depending upon how long this line is, one, that will affect that how much the person has to wait. That means how many people are before this guy, then how fast these guys are working. Okay, so these are certain parameters that will basically help to find that given a system that you are having where jobs are getting queued and waiting for getting served, how much time will it take to actually get out of that system or get served by that system. We can also find several different parameters with that, okay, which we will study thoroughly in the queuing theory classes. Okay, so let me show you a very simple diagram of a queue. Okay, so how does a queue look like? Very simply, a queue looks something like this. This is the buffer of the queue, or this is actually the queue. Then this is the server. Okay, so you have arrivals here. These are arrivals of jobs, arrivals of packets, etc. Okay, so they will be in this queue. They will be waiting in this queue. This guy is the server. That means who is serving these jobs which are arriving, and then after that they will depart from the system. That is departure. Okay, so you can think of any scenario in your mess counter, days in which you have like something that takes long time, maybe dosa or something like that, then you have a long queue. You can consider that system as a queue. In your registration counters, when you were you get a line and then the person works on the counter, that is also one example. In the banks, when you wait for your turn, that is also a queue. Okay, so anything that you see that is having a queue, a server, and the corresponding properties there, that you can analyze with the help of queuing theory. Okay, so now what we are going to study is we are going to study about input queuing. So what do we know about input queuing? The properties, that is the buffer that we are having at the input port and the line card capacity. That is going to affect that how the switch utilization will or how much the switch utilization will be. Okay, so with the help of queuing theory, we will study about the queuing analysis, or we'll study about the theoretical utilization of input queuing. Okay, so next class I will start with queuing theory, but before I go ahead and start with queuing theory, I would like all of you to just go ahead and check out exponential distributions, basic distributions that you have studied probably in your 12th or in your 12th or in your first year BTech courses.